Okay. So, in the last class whatever we were describing is we are trying to show that if we do a simplest form of modulation which we are calling as DSB SC, that DSB part is clear, probably SC is still not clear, that will be clear after some discussion, some amount of discussion. But that particular modulation which is the simplest of amplitude modulation, where just we multiply a signal MT with cos omega CT. So, we have shown the frequency domain response of that. So, basically it will be just centered around FC, and that same criteria will be coming, that this will be MF minus FC and this will be MF plus FC, and of course with half. Okay, so it will be centered around FC. So, this is the frequency domain representation, and the corresponding time domain representation we have understood from this particular thing, that it's a carrier whose amplitude is instantaneously varying with respect to the message signal, which is a slow varying signal according to our assumption. Here also that assumption comes into picture, because FC has to be much bigger than B, which is the highest frequency component that the message signal has. So, therefore, that will be much slower varying signal, and amplitude of that carrier will be slowly varying accordingly. So, that means that MT should be observable in the envelope of the signal that is being transmitted. So, it is a cosinusoidal signal, only the envelope will be tracing that MT. Okay. So, what is happening? There is a possibility that MT might be positive or MT might be negative, like over here. So, this is the crossover point, right. Beyond this MT is positive, just after this MT will be negative. So, what will happen in the carrier? So, the carrier, that cos is going up to this point, it is positive, immediately after this point it will be negative. So, in the frequency, means in the phase of the carrier, what will happen? From positive to negative immediately it jumps. So, there should be a 180 phase shift immediately, right, because the amplitude is just getting, means from positive to negative. So, therefore, in the carrier phase there should be 180 phase shift. So, wherever there will be zero crossing in this DSB SC in time domain, if you just observe the signal, you will always see a 180 phase reversal. Whichever way, whichever phase it cuts over there, it will just be a 180 phase reversal. So, every point you will be getting that. That has a huge implication. We'll see that. That makes the demodulation very costly. We'll come across that, and that's where the suppressed carrier and non-suppressed carrier comes into picture. We'll come to those things. But we have, from the time domain, we are just trying to analyze whatever is happening. Okay. So, there is we know as many times there will be this zero crossover, that many 180 phase reversal will be happening. If this was also having a pattern like this, there also we would have observed similar thing. So, it will be like this, the envelope will be just like this, and again if things were coming out like this, there will be a 180 phase reversal immediately. Okay. So, as many zero crossover will be happening, that many phase reversal will be happening. So, we have understood what is the modulation, right. What will be corresponding demodulation? That means I will be receiving this MT cos omega CT signal from the air through my antenna. Now, I have to get back my MT. Okay. So, how do I get that? Very simple operation, another multiplication will give me that. If you just see MT cos omega CT I am getting, if I just multiply it with another cos omega CT locally generated, what will happen? So, this is, if I just take half MT, this is 2 cos square omega CT. Cos square omega CT can be written as cos 2 omega CT, right. Right, we can just write this. Immediately what we get, we separate these two out, I get half MT plus half MT cos 2 omega CT, fine, this is what I get. Now, just see this signal. Now, you will appreciate why this Fourier transform and all those things were so important, why time domain and frequency domain we have to observe this signal. Let us try to do a Fourier transform of this signal, of this composite signal. Let us call this as phi t, and then I wish to evaluate phi f. What is phi f? So I have half over here, so that should be half mt, the Fourier transform should be mf, and this is multiplied by cos 2 omega c t. So therefore there should be a frequency shifting property. So I can write half, and then this particular part should take me to cos f plus fc, sorry, not cos, m f plus fc plus m f minus fc, right? Is this fine? Okay. So I will get that particular thing, but there should be a half also coming out of this one, because this, whenever I multiply by cos there should be another half, so this must become 1 by 4, right? Sorry, there is 2 omega c, so it should be 2 fc, okay, fine. So if I now just plot this frequency response, how it will look like? So this is, suppose my mf was something like this, so this is mf, half mf, so this is that half mf, and at 2 fc there will be 1/4 of mf minus fc, and at minus 2 fc there should be 1/4 of m f plus fc, fine, 2 fc, yes, fine. Now it is very simple, you can see that just by putting a filter I can extract my signal back. I will be putting a low pass filter over here which has a cutoff frequency which is much lower than this 2 fc but bigger than this b. Okay. If I just employ a filter like that, I will be getting my half mf back, which has a Fourier inverse transform which is half mt. So I will be getting this signal back. Okay. So immediately you can see my demodulated circuit is almost ready. What I need to do in demodulator, whatever modulated signal mt cos omega ct I will be getting, I will do another multiplication with cos omega ct. Whatever I get, I pass it through a low pass filter. Even the filter design is also known. The cutoff frequency must be, suppose the cutoff frequency fc cutoff, okay. So that must be bigger than b, we should not say much bigger than b, but that must be lesser than this 2 fc at least. As long as I am doing that, I will be getting my signal half mt over here, because this part will be rejected. So very nice, we could realize, see this is the importance of signal and from signal to system. That is why probably we have devoted so much time in doing frequency response, Fourier transform, how to see a signal in frequency domain. So those are the things, just giving us tools, enough tools to actually manipulate the signal and then understand what kind of systems I should put, so that whatever I wish I will be able to achieve that. So basically your modulator and demodulator is now ready for this DSB SC. Of course we still have not characterized what this multiplier circuit will be, how do I achieve a multiplication, okay. But we have now understood that if I know how multiplication has to be done, I need a multiplier circuit followed by a low pass filter that will make my demodulator. I need, in the modulator I need just a multiplier circuit, nothing else, okay. So now let us try to see what are the difficulties over here. The first difficulty that comes out is generating this one. That is a big challenge, because if you see very carefully, the frequency and of course the phase also, we are not writing the phase, these two has to completely match over here, then only that cos square 2 omega c will be coming out, and then only the Fourier transform will give me very nicely mt. Later on we will prove that if there is a phase drift or frequency drift and if we multiply these two, I have a chance of not getting anything over there. Okay. So, we have to be very cautious about generating this local cosinusoidal. That has to be completely in sync with the carrier by which the signal has been originally modulated. The problem is that nobody will give me that signal, right, because if the modulator and demodulator are sitting at the same place, what is the point in doing communication? Because when we wish to do communication, we wish to transmit it over a longer distance. If I know that same carrier I can give in both places from the same circuit, then probably my modulator and demodulator are already sitting in the same place, or otherwise I have to separately again communicate the carrier as well, right, to a long distance. So, just to send my message over a carrier, I have to again transmit my carrier along with it. That is one difficulty. Okay. The second difficulty is, even if I try to send my carrier, there is a possibility that this modulated signal and the carrier, because they are going through the channel, they might go through some frequency and phase drift. It might happen due to Doppler effect, due to other effects that are there, due to the channel effect mostly. So, there will be a drift in phase as well as frequency of the carrier signal, and that will be random, as well as the modulating signal. So, if I wish to really, even if I have that carrier and I am transmitting along with that, there is a possibility that these two are going through different phase and frequency drift, and at the end they are not in sync in terms of frequency and phase. Again, if I multiply, I will not get the proper representation. So, what I have to generally do, that this particular signal that I am getting, already I know that it already has, of course, a contaminated cosinusoidal. Can I extract that carrier out of this? If I can do that, from there if I can generate this cos omega ct, then I am fine. So, that is called the carrier recovery. There is a, there will be in this course only, there will be a few classes devoted towards that how do we do that carrier recovery. That is a big circuit again. It must be locked with the incoming frequency and phase, that is termed as phase lock loop. We will see those circuitry, but that is the part which is required, otherwise your demodulation will not be good. So, that is the difficulty we are having in this particular modulation scheme, that we need to have another carrier which is completely in synchronism with the incoming carrier frequency and phase. This is the one difficulty that we have. That means the receiver design becomes little more complicated, because we have to do this carrier recovery on top of this whole thing, right. So, if I now ask, when we are designing a system, is this desirable for, let us say, a broadcasting kind of system. Okay. Broadcasting means like the radio transmission, we had those Vividha Bharati and all other things, where we used to just transmit something from a big antenna, okay, and that was broadcasted to everybody. Everybody was listening to same voice. Okay. So, this was broadcasted, and everybody must have their own receiver and they must detect it. Okay. In that kind of thing, I can actually make my transmitter a little costly, because that is common to everybody. That cost will be shared among all the users. Whereas there are multiple users who are willing to receive this signal, their receiver must not be very costly. Okay, because if the receiver is costly, that cost directly will come on the user. So, in a broadcasting system, generally my target should be that the receiver is little bit simplified and the transmitter probably is little more complicated. Okay. Why I am saying all these things? This will give me another design direction where I will probably take out this difficulty of getting this carrier recovery circuit into it and then multiplying it. So, this entire stuff I will take out, and I will employ another modulation scheme which will be just a simplified modified version of this, where the receiver will be becoming very simple, but the transmitter will be little more complicated. We will show you what kind of complications you will be having in the transmitter. Probably transmitter will be a little less efficient, okay. But that is pretty obvious. whenever we have one-to-one communication, probably this is better, because then I cannot make the transmitter very costly, because it is one-to-one communication. Again, if I increase the transmitter cost, that will come to the user. So there I need to have a balance, that transmitter receiver must be almost similarly equivalent complex. So there will probably we can employ this particular technique. So that is why that short range radio communication people have used SSB, DSB, double sideband suppressed area, this particular modulation technique that we are discussing about. So whenever we have one-to-one that short range radio communication, which is not broadcasting in nature, there we can employ this kind of technique. Okay. Now let us try to see that we have talked about this demodulation. Now let us first for DSB-SC, okay, let us try to see what are the different kind of modulator that we can generate. So we have talked about that multiplier. Let us say there are, if you go into market, you will see that there are multiplier chips with differential amplifier and all those things. It's a little complicated. Okay, so we can always employ a direct modulation by that technique, but there are other techniques, and which we will be discussing, other very simplified techniques to do modulation. We will discuss those things. The first one is called the nonlinear modulator. So in that case, we will be using a nonlinear device. Okay. What do we mean by nonlinear device? That if I give a input xt, the output will just not be a linear scaled factor of this. Okay. What will happen? It will produce some square term as well. It is just a nonlinear device, so output will be means showing nonlinearity with respect to the input. So suppose my xt is this and output is yt, and if I have yt following this relationship axt plus bx square t, that is the simplest nonlinearity we can get, that is the quadratic one. Okay. So we can also have other nonlinearity or other higher order like cubic, so it will be having some another constant c into x cube t or so on, higher polynomial also. But we can easily get this quadratic nonlinearity and realize this by some devices which we all know, like transistor or diode. Okay. So they, if you see their characteristics function, that has a nonlinearity, because the characteristic function generally goes like this, right. And if you bias it in certain region, you will see that it will follow quadratic nature. Okay. So this kind of nature. So if you give input, output will be just in a quadratic form with some a and b, that will depend on the diode characteristics. Okay. But if we have a nonlinear device which is let us say a diode properly biased, so that we get a quadratic nonlinearity into it, and that is this device. And now if we connect this in this fashion, so my two input, if you know, are mt and cos omega ct, I need to produce a multiplication term. So what I do is something like this, I have two adders. So these are just you can put them as op amp adder. Okay, it will just add the signal. So this goes over here, this comes over here, this is actually this is a adder actually, sorry, and this is a subtractor. So it is plus and minus. I get x1t over here, x2t over here, and then I pass it through a nonlinear device of this nature. Okay. Again I pass it through a nonlinear device of this nature. So I get y1t and y2t. After passing it through this, I pass it through another adder, or I should call it subtractor, and then whatever I get, I pass it through a band pass filter centered around plus minus omega c or fc. Okay. And the output I will be getting will be proving that it is actually 4b mt cos omega ct. If I adjust my b to be 1 by 4, then it is actually mt cos omega ct, whichever is our target. Okay. So how this works, it's very simple. If you just do those algebraic manipulations. So if I have this x1 and x2t after nonlinear device, so suppose this is zt. What is zt? Zt is y1t minus y2t, whereas y1t is actually a x1t plus b x1t square minus y2t is a x2t minus b x2t square, right? Or I can write as a x1t minus x2t plus b x1 square t minus x2 square t, right? Now what is x1t? x1t is mt plus cos omega t, and what is x2t? That is mt minus cos omega t ct. Okay. So x1 minus x2t will be just mt will remain, right? So that should be 2 mt, and this is a plus b whole square minus a minus b whole square, because x1t is, if this is, or let us say I should not say a, let us say c and d. So c plus d whole square minus c minus d whole square, that should be 4, right, c into d. So therefore it should be 4 into b, c into d is mt into cos omega ct. So mt into cos omega ct, right. Now what we are doing? Now the frequency domain term will come into picture. So this mt, if I take it into frequency domain, that should be mf, and this if I take into frequency domain, that should be m plus mf, mf plus fc and mf minus fc. If I put my band pass filter around fc, then this term should pass through and this will be not going through it. So therefore at the end only this term will survive, which is this, right. So we can see we can actually devise a multiplier circuit by 2 nonlinear device and 3 adder. Okay. Adders are very easy to devise. Just take a op amp and you can make an adder, right. So 3 op amp and 2 nonlinear device properly biased, let us say diode, properly biased, so that we get this quadratic relationship immediately, and a band pass filter. Again band pass filter can be designed using op amp and some active filtering. Okay. So that's, now you can see that's the multiplication circuit. So this is one way of doing multiplication. There is another way, that's called the switching modulation. So we are just trying to show you which are the devices that can be employed to do this modulation, right. So for switching modulation, what we will be doing, we know that a particular transistor or CMOS circuit can work as a switch. So in the gate of a particular this switching transistor, if we just put a signal like this, which is having, let us say, plus 5 volt for half the duration, and it is being 0 for half the duration. So what will happen? Whenever this is being put in the gate, it will be on, so it will pass the signal. So if I just put in the emitter to collector, if I just put my message signal, so whenever at the gate it is getting plus 5 volt, it will be on, then that signal will be passing through it, and whenever it is off, that will not pass through it. So if I just put a resistor across that, if I take the voltage, I will see that it gets switched. So basically if my signal is something like this, and if I just switch it through this, so whenever this part is on, the signal will follow, rest of the part it will be 0, again the signal will follow, rest of the part it will be 0. So basically what is happening, my message signal is getting switched through this pulse. Okay. So almost what we are doing, message signal multiplied by this pulse. Okay. So if I represent this as Wt and this is Mt, I can actually connect this Wt in the gate of that switch or transistor, and in the emitter to collector I can put a resistor across which I will be taking the voltage, and I across the bias this one and emitter I can put my empty signal. Okay. So then the output of the resistor will be this modulated signal, right, or whether it is modulated or not I do not know, it is a switched signal, right. Now basically that output will be just multiplication of these two, as I can see. If this is I put this as 1, then immediately it will be just a multiplication. Okay. So I get my output, which we say phi t is just mt into omega t. But the omega t, if you carefully see, that is a periodic signal. So I can do a Fourier series analysis. This is where you can see all those techniques that we have used will actually be used over here. So omega t, I can just expand it in Fourier series. So you can just do it. It's represent this one as this, which we have already done probably, something like this. Okay. So it's, if this is overall t, this is, sorry, this is t and this is minus t by 2, this is t by 2 and this is minus t by 2, and with this period it gets repeated. Okay. So this one, if you just do Fourier series analysis, you can represent it as this half. So that means the DC part will be half that coefficient. Next coefficient will be 2 by pi into cos omega c t. The next coefficient 2 omega c t will not be there. It is the 3 omega c t part which will come, 1 by 3 cos 3 omega c t plus, so it gets alternative plus and minus. So 1 by 5 cos 5 omega c t and so on. Okay. So basically it has all the odd frequency harmonics and the coefficients will be alternatively plus minus, and the corresponding coefficient becomes 2 pi into 1 by whatever the frequency, whatever the harmonics. Okay. So this is what omega t is. Therefore my phi t will be, immediately I can see, I multiply this. So half mt plus 2 by pi mt cos omega c t minus 2 by pi into 1 by 3 mt cos 3 omega c t and so on. Okay. Again do a Fourier transform of this, because phi f I wish to see. So if I do a Fourier transform, I can see there will be some part at baseband. Next mt cos omega c t, so that should be around fc. Next will be around 3 fct. Now if I just employ a band pass filter around fc properly designed, then I will be just getting this signal, all other terms will be neglected. So immediately I get my modulator, because this is mt cos omega c t. Okay. So if I just, so basically what I have to do, I have to put a switch which has two input, one is that wt and the other one is that mt. After that whatever I get, that is this phi t, must be passed through a band pass filter centered around plus minus omega c. Whatever I get, that is actually 2 by pi mt cos omega c t, right. So that is another way of doing multiplication. This is called the switching modulator. So in the next class probably we will be discussing more about the relative advantage and disadvantage of all this circuitry.